are watching 99.9 Engineering Station. So student, today we are going to understand the temperature dependent term in the rate of equation and also understand the key concept of activation energy and Arrhenius equation. So till now, if you are not subscribed to my channel, subscribe it, otherwise you will not get any type of notification from my side. And one more important thing is that you have to follow me on Telegram, because in Telegram I used to post many important questions, numericals, short notes and many more things. So follow me there and subscribe my YouTube channel. So without further ado, let's get started with the lecture. So student, in the previous lecture we study about the rate of reaction factor which is affecting the rate of reactions. So these factors are composition or concentration, temperature, and the lastly is the catalyst. Okay, so the composition or concentration part is already we study in the previous lecture, and today we are going to understand the temperature dependent terms, and lastly the catalyst term we are going to study in the second CRE second, that is in the heterogeneous section. Okay, so let's start with the temperature dependent terms of the rate of reaction. So first we write the reaction, that is AA plus BB gives CC plus DD. Here the small ABC is the stoichiometric coefficient. If we write the relation between the stoichiometric coefficient and the rate of reaction, it will be a minus RA upon A is for the reactant A, and for the reactant B will be minus RB is equal upon B, and for the product RC upon C and the RD upon D. These are, we are taking negative sign for the reactant part of the component, and we take positive rate of reaction for the product side. Okay, so similarly we are going to solve some one of the little bit very simple equation. For example, is A plus 2B gives 4P. Okay, in that case the rate of reaction relation between the stoichiometric coefficient and rate of reaction will be like that: minus RA upon 1 minus RB upon 2 is equal to RP upon 4. So we are taking the negative sign for the reactant and the positive sign for product, and we simply divide the coefficient, stoichiometric coefficient, with the rate of reaction. So this is how we write the rate of reaction in terms of the relation between the stoichiometric coefficient. Okay, so I already said that the rate of reaction is the function of the temperature and the concentration. Okay, so rate of reaction is the function of temperature dependent term and the concentration dependent term. So we write it as a mathematically like minus RA is equal to KCA. Okay, here the CA is the concentration dependent term and K is the temperature dependent term, and we call it as a reaction rate constant. Okay, we call it as a reaction rate constant or reaction rate coefficient. So reaction rate constant is we get from the Arrhenius equation, which is given by the K is equal to K naught e to power minus E upon RT. Okay, this is very important equation of the Arrhenius equation, that is K is equal to K naught e to power minus E upon RT. Here the K naught is the pre-exponential factor, E is the activation energy, and T is the temperature in Kelvin. Okay, so what is activation energy? Basically the activation energy is the minimum amount of energy required by the reaction or reactant to start the reaction. Okay, it is a minimum amount of energy which is required by the reactant to start the reaction. Okay, so basically this term activation energy in this topic is very important, and we are going to study the variation of activation energy with the rate constant, reaction rate constant. Okay, so if we take logarithmic in the both the side of the Arrhenius equation, the equation become ln K is equal to ln K naught minus E upon RT. Okay, so this equation, when after the taking a logarithmic simple mathematical calculation, and we get this equation which is similar to the straight line equation, that is y is equal to mx plus c. You can see that this equation is very much similar to the, almost similar to the y is equal to mx plus c. So this is about this equation. Now this is all about the only this equation when we are considering only one temperature or concentration, same concentration. But if we have a different temperature condition, two different temperature condition, what will be the equation for that? But the concentration will be same. In that condition, we apply the equation is like that: ln K2 upon K1 is equal to E upon R 1 upon T1 minus 1 upon T2. Here the temperature we are going to take is two different temperature, but the concentration is same and the activation energy is same in the both the temperature condition. Okay, so this equation is also very important in point of view of solving the gate numerical. Okay, so now the another thing we are going to study about the relation between the reaction rate constant and the stoichiometric coefficient. You can see here I have write it Ka upon Ka is equal to Kb upon B is equal to Kc upon C is equal to Kd upon D. This equation is almost similar to this equation of the rate of reaction. And how we get this reaction, this type of equation? Like suppose we have a reaction AA plus BB plus CC plus DT. Okay, we have a reaction like that. So we can write the rate of reaction of the each of the component, like RA is equal to Ka Ca Cb x to power y, xy. Similarly Rb is equal to KBCA XCBY, RC is equal to KCCA XCBY, RD is equal to KDCA XCBY. ठीक है, these are the equation number 1, 2, 3 and 4. If we divide equation 1 and 2, what will happen? Minus RA upon minus RB, and which is equal to the A upon B, and this equation become after dividing is equal to Ka upon Kb. So by simply cross multiplying we get the equation, that is Ka upon A is equal to Kb upon B. So from here we got the relation, that is Ka upon A is equal to Kb upon B is equal to Kc upon C is equal to Kd upon D. See, so this is also very important concept or related to the rate of reaction. Okay, now now as we know that the Arrhenius equation, according to Arrhenius equation, the equation is K is equal to K naught e to power minus E upon RT. So we rearrange this equation like that, that is K is equal to K naught upon E to power E upon RT. Okay, here if we study the relation with variation of activation energy with the reaction rate constant, what will be the concept? That is we produce a three concept, that is number 1, number 2 and number 3. First one is, if we increase the activation energy, what will happen? The K value is decreases. Like if we increases the activation energy, the whole term is increases. Okay, if this term is increases, it means the K value is automatically decreases. Okay, after dividing it. That's why the rate of reaction is also reaction, and it become also decreases and becomes slower rate. Okay, so the concept is that when we increase the activation energy, the value of the reaction rate constant decreases and the reaction rate of reaction is also decreases, that is slower, it becomes slower rate. Okay, another thing is that if we decrease the activation energy, the term, that is K, is increases. Okay, and in the case of temperature, if we increases the temperature, then the reaction rate constant is always increases. Okay, So these these 3 points are very important for solving the gate problem, and one of the, trust me student, only most of the time in the gate exam the concept related, the question related to this concept is always coming in the last classes, in the last question paper. Okay, the another thing which we are going to understand in this lecture, that is single reaction and multiple reaction. So basically the single reaction is that type of reaction in which when we are choosing only one stoichiometric equation and the one rate of reaction equation for representing the progress of the reaction, in that case the reaction is single reaction. Okay, and in this multiple reaction we choose or we needed more than one stoichiometric equation and the rate of reaction for showing the progress of the reaction. In that case we needed a multiple reaction. Okay, so this is all about the multiple reaction or the single reaction. So here I am going to show you the multiple reaction, that is A gives the B and C. A is the reactant, which single reactant which produces B and C. Here B is the desired product and the C is the undesired product. Okay, so activation energy of desired product is E1 and the activation energy of undesired product is E2. So let's discuss the relation between the activation energy and the temperature of the favorable temperature of the reaction. Okay, so if the activation energy of the desired product is greater than the activation energy of undesired product, in that case the temperature, favorable temperature of the reaction will be maximum possible. Okay, maximum possible. And if the activation energy of the undesired product is greater than the desired product, in that case the favorable condition for the temperature is the minimum possible. So these 2 points is very important. It is used to solve many gate problem. Okay, so from today lecture we are going to, we got the 5 main concept, that is first one, second one, third one and fourth and fifth. So these 5 points are very important for solving the gate exam. Okay, so if you understand today's lecture, please comment down in the comment section and please share this video with your friends, family and other students. Okay, so that everyone get the advantage of this lecture. Okay, so have a nice day. Thank you and have a nice day.